morning. I and Meghna are the organizers for this workshop. Um, it's very heartening to see a lot of people here. There's been a fair amount of activity regarding game theory and computational social choice in India recently. A bunch of schools, a bunch of workshops. So in that kind of way, this was organized as well to kind of bring people together, exchange ideas and so on. We tried to leave some space for discussions and questions and so on. If you're not able to find time now, please feel free to mail us or any of the speakers with any questions or queries or any discussions you might want to have. I'm sure everybody will be very receptive. This workshop is over 2 days. There are lengths of talks. A slightly shorter one at about 25 minutes plus 5 minutes for questions, and slightly longer one, which is about 40 minutes plus 5 minutes for questions. In the conference, there were brownie points for questions. We don't have that, but we still hope that the sessions will be interactive. There are volunteers who will have mics. So, if you have a question, please raise your hand. They will come to you. You can ask your question. In case the mic cannot reach you while you're asking the question, I would ask the speakers to please repeat the question so that it can be captured on YouTube as well. IT Gandhinagar has put a lot of effort into organizing this and so on. So there's very little I can tell you about logistics. But if you have any questions, again, you can ask us, you can ask any of the volunteers. All of us will be happy to answer all of these. So let me not take too much time. Let's get started with the workshop itself. I'm going to ask my co-organizer, Meghna, start the session.
Thanks, Umang, and thanks thank you, everybody. Welcome all of you to this workshop on algorithmic mechanism design. It's my pleasure to have this introduction, and I'm glad to introduce Professor Uriel Feige, who actually needs no introduction. Professor Feige is a faculty at the Department of Computer Science and Applied Mathematics at the Weizmann Institute. His research interests span diverse areas in theoretical computer science, including but not limited to approximation algorithms, hardness of approximation, and algorithmic mechanism design. He has been a recipient of several prestigious awards, including the Gödel Prize. And today he'll be talking to us about a bidding game for allocation of indivisible goods. So over to Professor Feige.
Is it working? No, I don't. Well, then. I know. So now it's supposed to be on. Okay, good. Good morning. It's a pleasure being here. I'm enjoying my time here and looking forward to this workshop as well. So the title of my talk is a bidding game for allocation of indivisible goods. So for those who saw my talk yesterday, the first few slides would be a repetition. Doesn't work. Do it from here.
No, it is not. No, it is not. Just a second.
Oh, I can do it from. If it doesn't work, I'll try this. No.
Not there, right? You have to put it here. Yes. Yeah, I think the pen. Yeah, could you please?
Now it works. Okay, good. So we'll consider allocation of indivisible items. So in our setting, which is a standard setting, there will be n agent and a set capital M of m indivisible items. In this talk, there will be goods, which means items that agents want to receive. And an allocation is a partition of the items into n disjoint bundles, where bundle j goes to agent j for every j. So in this simple example, the red agent got 2 items, the sun and the moon, and the green agent got 2 items as well. So this is an allocation. And in our setting, there are no payments, so the agents do not pay to receive the items, or they do not transfer money between themselves. And so when we want to allocate those items and we think of mechanisms of doing so, a common mechanism is to use things like auctions to allocate items or selling them or things like that. We cannot do this here. Examples of such settings are allocation of housing units to eligible residents, so allocations of seats in the parliament to political parties according to their size, how many seats each party gets, dividing an inheritance that contains items of sentimental value that you cannot divide, like a ring or things like that, handling student registration to courses of limited capacity, and so on. So what is the input to an allocation problem? So we have a set of items. This is part of the input, the set of the agents that will participate. And we have another term, part of the input, which is the entitlement of each agent. Now, like we want to divide the items based not necessarily in equal parts to each agent, it depends on their entitlement. So for example, if you're in a situation of dividing an inheritance, it could be, let's say that the wife inherited half of the property and each of the children inherited 1/4 or things like that. They don't need to have equal entitlement. So the way we model it, each agent has an entitlement bi, which is a number between 0 and 1, and the sum of these numbers has to equal 1. A special case is that of equal entitlements in which each agent has entitlement 1 over n, as there are n agents. And so this is the input, which are the items, the agents, and their entitlements. And the output that we want to produce is an allocation which is in some sense fair. So the agents judge it to be fair. So the entitlement is just numbers, so let us say what our interpretation of these entitlements is. So first, it's monotone. The higher entitlement you have, you're entitled to get more. It's better to have higher entitlement. If an agent has entitlement 1, it means that that agent should get all the goods, like is entitled to everything, and the other agents have entitlement 0. And we assume that the entitlements grow in a linear scale, so defining it is a bit tricky, but one way of saying it is that if agent J transfers her entitlement to agent I, then the new entitlement of agent I is the sum of the entitlements. Or for example, if someone, let's say a parent wants to give his entitlement to his 2 children, then the sum of the entitlements that they get is the entitlement that the parent had. Let's say if it's okay. So this is the setting. And now when we seek a fair allocation, there are certain notions of fairness, and they are different from each other. So one is just procedural fairness. We design an allocation procedure, an algorithm that allocates the items, and we want the procedure to be fair. So sometimes this is what is used. Let's say in some situations when you want to, like, say, allocate, I've seen this happen, let's say in Israel, housing units to eligible residents, you pick a random order over the agents, and each agent in her turn chooses a housing unit, let's say. So here we just say the procedure appears to be fair, all agents are treated equally, we don't care about the outcome. They can do with the right to choose whatever they want. That's their own business, what they do with it. The other kind of fairness notion would be ex post fairness. We look at the final allocation and ask, is it fair, yes or no, according to some criterion that we define. And there's also the notion of ex ante fairness. This is when we have a randomized allocation algorithm that produces a distribution of our allocations, and we want the whole distribution in some sense to be fair. As an example, suppose there's just one item and two agents, then you can decide, let's say, toss a coin and decide who gets the item. So ex post, it's not going to be fair because some agent would get nothing and some agent would get everything. But as a distribution, this is fair. So that we have these three classes of fairness notions. And the ones that we'll focus on in this talk are two of them just. So one is procedural fairness and the other is the ex post fairness. So we'll describe a bidding game. So this is an allocation mechanisms for agents of arbitrary entitlement. And we did not formally define what procedural fairness means, but looking at it, it looks as if it satisfies what we would want procedural fairness to satisfy. And regarding ex post fairness, so we define it's sort of a game. So the outcome depends on what the agents do. So we cannot say that the outcome would necessarily be fair. But what we do, we show that agents have strategies such that if they follow them in the game, they get something that would appear fair to them. The items that they get would appear fair according to some standard fairness notions. Okay, so they have the option, if they want to reach a fair allocation. Those agents that want to, and those agents that don't want to can do whatever they want. Yeah, so this would not help the agents that do use these strategies. And for this game, we will not analyze ex ante fairness. So we'll only consider the procedure as being fair and the final outcome if you follow a safe strategy.
The agents that do follow the strategies are guaranteed.
So just to explain again, so a safe strategy, so this was the question, is a strategy such that if the agent follows it, no matter what strategies the other agents follow, that agent who follows the strategies has some guarantee of what he's going to get. Okay. So this avoids questions like truthfulness. So I don't care if I follow the safe strategies, in a sense, if I only care about the fairness notion, I don't care if other agents are not truthful about their valuations or whatever they do. Like the game does not dictate what agents have to do. So they can do whatever they want. I don't care what they do. And I can decide also if I see that I have a better strategy than the safe strategy, it's okay if I take it. I mean, so the issue of incentives, there is an incentive to play the game as well as you can. That's kind of the incentive. And I should say that this also implies that in every equilibrium of the game, you get at least as much as you get in a safe strategy. So if you want some solution concept for games like equilibria, then they guarantee good outcomes for the agents. Okay, so the game, we refer to it as the bidding game. It's a version, I mean, similar games in other contexts were previously defined, so it's not entirely new. So in this game, it proceeds in rounds. And before the game starts, each agent gets a budget equal to her own entitlement. So in this respect, it's fair because the initial budget that you get depends on your entitlement. And then in every round, each agent can make a bid, and the bid has to be not higher than her remaining budget. So you cannot bid more than your budget. The highest bid wins the round. And then the agent who made this highest bid can start selecting items. For each item that the agent selects, he must pay the bid that he made for that round. So if he selects one item, he pays his bid. If he selects two items, he pays twice the bid, and so on. And then the round ends when the agent stops selecting. And then we start a new round with new bids. And the new winner can select items and so on. And the game ends when no items are left. It could end when also no budgets are left, but if you think of it, this would never happen because the last agent to hold the budget would then start giving bids which are like a very small epsilon and win all the remaining items. So basically the game would end when no items remain. So any questions about the game? Yes, please. No, you make like a bid for the right to be the person who chooses in that round. So you make a bid like to be the winner of the round. The highest bidder becomes the winner of the round, and once that agent is the winner is allowed to start picking items and pay for each item the bid that he made. Okay. Yes.
So how do you items
So the game does not say how the agent has to pick the items, but in the strategies that we suggest for the agent, we would suggest that he picks the item that he values most. So we can do, the agents can do whatever they want. The game does not dictate it. It comes only in the initial budget, and after that, you forget about the entitlement. If you have higher entitlement, you have a higher initial budget, so you probably can win more rounds and select more items because you have higher budget. You can give higher bids.
I see. Thanks.
Yes.
Say the ratings on the right to select.
Yes.
How is the price for each of these computed?
So the bid is for the right to select. It doesn't matter for our purpose, like if the bids are made simultaneously or one by one for each agent, doesn't really matter. And then you just look at all the bids in that particular round, and whoever made the highest bid, let's say breaking ties arbitrarily, we don't really care how, this is the person who's allowed to select items in that particular round.
That is the bid for every item.
For every item that it takes.
The same price.
The same price. Same price for every item. Yes.
Just a clarification. So can you give an example of a mechanism which is procedurally fair and not like which is ex ante fair and not procedurally fair? Or ex post fair and not procedurally fair?
Okay, so what's the difference? I think a big difference between procedurally fair and ex ante fair. Ex ante fair would usually be with respect to some class of valuation functions. And if you're not in this class, you don't know what will happen. Procedurally fair in a sense says, I don't care anything about your valuations. Maybe you don't even have valuation functions. I don't care. Like this is the procedure. That's the way I look at it. Because in a sense, it's an assumption that agents really have valuation functions. Maybe they don't, in a sense. In real life, you don't really always know the values of item for you. Maybe if your valuation function is not stable, like 1 minute you think I like this more, next minute you think I like this more. So it's really, we should remember that valuation functions are just assumptions. We don't really know if agents have them. So procedurally fair avoids these questions completely. Yeah.
Maybe you address this very soon. But the point here is that you're in this bidding process, you're not looking at like what the valuations of the common knowledge or information about like valuations of others and
Yeah.
number of is not relevant.
Yeah, so agents don't know about valuations of other agents. They don't know if even other agents have valuations. Maybe the other agents are just adversaries who just want to prevent them from getting something. They don't know this. Yeah. So, okay, so let's go on. Okay, so what ex post fairness notion we'll be looking at? So recall that we're in the case of unequal entitlement. The more common fairness notions are the ones, let's say, in the equal entitlement case, and one of them is the maximum share. So we can apply it whenever the entitlement of an agent is 1 over an integer, 1 over k, and then the maximum share is like the agent would play this mental game, partition the bundles into k, partition the items into k bundles, and get the worst bundle among these k. So as if there are k agents like him, what's the bundle maybe that is entitled to receive? The worst in the best k partition. So this is a good definition when the entitlement is 1 over an integer, and the question is, what would be a good definition when the entitlement is not something like 1 over an integer, let's say between 1 over k and 1 over k plus 1. So the fairness notion that we use is the any price share. So the maximum share is like what you get as a cutter in a cut and choose game. You cut the set of items into k parts and get the worst part. So, and the any price share is what you get as a chooser in a different game, price and choose game. So let me show this game. So in this game, there's an adversary who tries to prevent you from getting something good. The adversary knows your valuation function and tries to prevent you from getting something good. So the adversary can set prices on the items such that the sum of the items, sum of the prices is equal to 1. And then you can choose the best bundle that you can afford with your entitlement, and your entitlement is your budget, BI. So you're allowed to choose a subset of items such that the sum of their values is at most BI. So this is the definition. So note there are no other agents. It's just like the set of items and the agent, and no other agents are involved in this definition. Unlike, let's say, definitions of NV3ness or things like that, where you also discuss what other agents get. So as an example, suppose you have an additive valuation and your entitlement is 2/5, so it's not 1 over an integer, so 0.4. And there are 5 items, 2 large items, A and B, of value 7 each, and 4 small items of value 5. So what would be the any price share in this case? So we have to set prices to the items and to prevent the agents from getting a high value. So what prices we can set? So we can set these prices, they sum up to 1. And under these prices, the agent can buy either with a budget of 0.4, either 1 large item or 2 small items. So it's better to buy 2 small items. And then the agent can get a value of 10. So this vector of prices shows that the APS is not more than 10. It doesn't mean that the APS is equal to 10, because maybe there's a different vector of prices in which the agent cannot even get 10. So to show that it is equal to 10, we have a somewhat like a sort of a dual formulation of the APS. So the way it would work here, we can make up 5 bundles which are overlapping. So each 2 consecutive items would make up a bundle. So this makes 5 bundles, like A and E also make up a bundle. So no matter what price the adversary sets on the items, since each item appears in 2 of these bundles, so the total price of all these bundles combined would be 2, because each item appears twice and the sum of the prices is 1. So one of the bundles would cost no more than 0.4, and the agent can afford it. So the agent can always afford to get at least 2 items, and hence at least a value of 10. So the APS is exactly 10. So let me go over this quickly. So what I showed now was like an alternative. So the APS is a min-max definition with the prices, a max-min definition with this partition into overlapping bundles. And this max-min definition also implies that the APS is always, if the entitlement of the agent is 1 over an integer, the APS is always at least as large as the MMS, the max-min share. So getting an approximation with respect to any price share is, even in the case of equal entitlement, is better than getting approximations with respect to the max-min share. Okay, so what will we show? We'll show that in the bidding game, we'll safe started. Sorry. So, okay, the question was about computing the APS. So let's say it depends on the class of valuations, of course, but let's look at additive valuations. So in additive valuations, computing the MMS is NP hard and strongly NP hard. Computing the APS is easier. It's APS hard. You can, it's something similar like, and with demand oracles, you can compute it exactly also. So it's easier than computing the MMS. Okay, so safe strategies for the bidding game. So we'll consider 3 classes of valuation functions. One is additive, when the value of a set of items is the sum of values of the items in the set. The other is submodular functions. So these are functions in which the marginal value of an item is not increasing, or we should weakly decreasing, the more items we already have. And there are the sub-additive valuations in which the value of a set is never larger than the sum of values of its parts. So these are the 3 classes of valuations that we will consider. Okay, so for additive valuations, even in the case of equal entitlement, and even in the easier benchmark of achieving the MMS, this is not feasible. It's known that there are allocation instances in which in every allocation, some agent will not get the MMS. So this obviously also extends to the any price share. So we cannot expect agents to have strategies that give them the any price share, because there might not be any allocation that gives every agent their any price share. So we settle for approximations. So we say that we get a row approximation to the APS if the agent gets a bundle of value at least row times the minimum value that would satisfy the APS. Okay, so let's look at the symbol strategy. So in this strategy, we first scale the valuation functions of the agents such that grand bundle, everything combined, is equal to 1, all items combined. And assume for simplicity, this assumption will be removed later, that no single item has value larger than BI, which is the entitlement of the agent. So here's a safe strategy that achieves at least half of the proportional share, meaning the proportional share of the agent here would be BI. So it gets a value of at least half BI. So the idea is in every round, you bid the value of the highest remaining item after this scaling of values of items. If you have enough budget to bid for that item. If not, you bid your full budget. And if you win the round, you take one item, the one of highest value, and pay your bid, and then you proceed to the next round. So this is a very natural strategy. You look like, think of the value of the items as prices for you, and you just say, I want the best item I can buy with my budget, like, or the best item that is available, and I'm willing to pay its price. And if I don't have enough budget for this, I'm willing to pay my whole budget. So this is the whole strategy. And why does it give a good guarantee? So if you manage to spend at least half your budget, you got at least half the value, so you're okay. So the only question is what happens if you did not manage to spend half your budget? How could that happen? So really the only way that this could happen, if you think of it, so if you did not spend half your budget, but you spend less of it, then it means that the next item that is on the table is worth less than the budget, the item that you already got, so you can't really bid for it. So all your bids were really for the true values of the items. So if somebody else took the item, he had to pay your bid for that item. So the total value that the other agents can take is like their total budget, which is 1 minus BI. So you have less than BI. The total other agents took a total of less, at most 1 minus BI. So some items must still be left on the table and you can continue playing. So this is like a sketch of proof of why this is an approximation ratio of half. So if we do it without the assumption that no item has a large value, and we do it with respect to the APS, we get really that the approximation ratio is half, or really slightly better than half. So if you're entitled, the larger your entitlement is, the approximation ratio tends to 1. So if you have very large entitlement, you get almost your full APS. And if you have a very, very small entitlement, it tends to half the approximation ratio. So here you can get half of your APS. You can ask, can you do better? So the answer is yes. You can bid more aggressively and get 3/5 of your APS. And this is a more complicated strategy. So you scale the valuation function so that your APS is equal to the budget. This would imply that the total value of all items is at least 1. It can be more than 1 in this case. And now the bid is a bit more aggressive. You want to reach 3/5 APS. So if there's a single item that gives you this value, you bid your full budget and try to take it. If there are 2 items that give you this budget, you bid half your budget. And if you win, you take both of them and you get this value. And if neither of these cases holds, you do something more complicated, which I will not describe. And the proof is also quite complicated why you can reach 3/5 using this strategy. So using this strategy, we can reach 3/5 of the APS. Yes. And okay, so as was said here, this implies that an allocation in which each agent gets 3/5 of their APS exists. And that's the only proof we know for this. So we don't know of any other proof showing this. If we go to a more demanding class, submodular valuations, so these are valuations in which items have decreasing marginal value. So if S is a subset of a set T, so adding an item E, let's say, to the set S is more valuable than adding the item E to the set T. So here is the strategy that we have is a variation on the proportional bidding strategy, just with some scaling. So we scale first the submodular valuation so that the APS is equal to the entitlement. So this is the same thing that we did in the additive case. But then instead of bidding proportionally, bidding for each item we bid its value, instead we bid something like 3/2 of its value. We can bid a bit less the larger your entitlement is, but think of the entitlement as being close to 0. In this case, you bid 3/2 of the value. And we show that if we do this, then we get at least 1/3 of the APS. Slightly better than 1/3 as your entitlement grows. So why do we bid more aggressively in the submodular case than in the additive case? Because in the additive case, once we take an item, the other items that we did not take yet still keep their value. In the submodular case, once we take an item, the other items, in a sense, their marginal value can decrease for us because we already have something. And in submodularity, once we have something, other things are worth less than they originally were worth for us. And now, if we just keep on bidding the value that we see for the items, the adversary has enough budget to take all the remaining items, because we are bidding too low. So we need to bid more aggressively to compensate for that. How am I doing on time? More than 10 minutes, okay, good. So the last example would be sub-additive valuations, where the value of a set is never larger than the value of its parts, if you partition it into different parts. So this is like a recent result prepared for this talk. Okay, so it's written down, but it wasn't checked externally, so I hope it is correct. Okay. Okay, so now we do something different. We scale the sub-additive valuation function so that the APS is so that the APS value is 1 now. And now, depending on my valuation function, we set a target value t that depends on the valuation function. So for some valuation functions, it would be higher. For some smaller, it would never be more than 1. And it would never be smaller than log m over log m. Okay? So this is like you look at the valuation, and it's a property of the valuation function when it's sub-additive, but it's never worse than log m over log m. And then what you try to do is get a value of t in just one round. So how do you do it? So in each round, let nr, in round r, let nr be the minimal number of items, such that if I get all of them, I get a value of at least t, my target value. And then I bid bi over nr, my entire budget over nr, so that if I win the round, I can select nr items and reach a value of t. So if I win the round, I do that, get a value of t, exhaust my budget, and I'm out of the game. So this is the strategy. So obviously, if you do win a round, you get a value of t. And okay. And the question is, why would it be the case that you win a round? So this needs a proof. It's non-trivial, but and I hope there are no bugs. But okay. So the theorem is that indeed, if you set this target value this way, you will win a round. Okay. So this also, just as a remark, this also implies you can use it also in the equal entitlement case, and it's for all agents use this in the equal entitlement case. You can show that you get each agent gets at least log m over log m fraction of their APS, which, as we said, is at least as large as the MMS. So this is also an approximation for the MMS in the equal entitlement case, and it's better than, as a function of the number of items, it's better than the approximation ratios that were previously known. I should maybe remark that there are also approximation ratios for the MMS in the sub-additive case that depend on the number of agents, not on the number of items, and this does not improve over them. It improves only over those that depend on the number of items.
That's a reasonably challenging step, right, in finding it.
So so how would the agent bid? So we need to assume some access to the sub-additive functions that would allow him. So what kind of oracle suffices? Okay, so we can always say we have an oracle that suffices for this. Okay, but otherwise, just learning what your own valuation function is supposedly a computational difficult problem, but somehow this is like for theoreticians too, but somehow in real life, if it holds, then we're in trouble, I think. So we would like to assume that in real life you can somehow reason about your own valuation functions and say, okay, this is a bundle that I like, this is a bundle that I don't, and so on. Okay, so consequences of the bidding game. So in the set of indivisible goods, arbitrary entitlement, there always is an allocation in which all these events happen simultaneously. So each agent, if I have an additive valuation, I'll get at least 3/5 of the APS because I'll use a strategy that gives it. If I have a submodular valuation, I'll get 1/3 of the APS because I have a strategy that does it, and likewise with the sub-additive valuation. And in each of these cases, this is the best approximation ratio known even without the bidding game for these valuation functions. Okay, So we can do all of these simultaneously. Okay, so let me briefly mention also some additional results that are obtained through the bidding game. So one is that in the case of equal entitlement and submodular valuations, and with respect to the MMS, we have approximation ratios better than 1/3. We have 10/27. We have a bidding strategy that gives it. And this is the best approximation ratio known with respect to the MMS for submodular valuations. So another consequence of the bidding game. Another that I'd like to discuss is a different fairness notion from the APS, not to use the APS, but let's introduce the MMS hat. So let's say your entitlement is between 1/k and 1/k plus 1. So you round up your entitlement to 1/k, and you compute the MMS with respect to this rounded up value. So it's like an optimistic rounding of your entitlement. You say, okay, my entitlement was 0.4. Let's pretend it was half. How much would I be entitled to get in this case? So that's this MMS hat. And the nice thing about this MMS hat is any share notion that you can think of, if it is feasible, in the sense that there is always an allocation that gives the agents this value of the share, then it will never be larger than the MMS hat. And for additive valuations, it is tight. So for every valuation, there is a feasible fairness notion that on this particular valuation gives the MMS hat. So like it's the best possible upper bound on all feasible shares, all feasible share notions. So that's the best possible upper bound. And what we show is that there is a bidding strategy for the plain version of the bidding game. So in the plain version, if you win a round, you select just one item. You cannot select more than one, in which you get at least half of the MMS hat. We show that for some allocation instance with arbitrary entitlement, there is no allocation at all that offers each agent more than half of the MMS hat. So half of the MMS hat is best possible, even without using the bidding game, even if some central authority designs the allocation. And our bidding strategy is not explicit, like it uses some non-constructive argument to show its existence. And we show that algorithmically, you have a bidding strategy that gives you half minus epsilon of this MMS hat. Okay, so let me summarize. So we introduced the bidding game, which is an allocation procedure for agents of arbitrary entitlements. And to me, it appears procedurally fair, but I did not define what procedurally fair means, so we can discuss this. And then we offered safe strategies for the agents that give them ex-post guarantees if they want to use these strategies. So I do not describe it for some special easy classes of valuation functions. You get the full value of the APS, let's say for unit demand. For additive, submodular, and sub-additive, we get, using this bidding strategy, the highest fraction of the APS that is currently known. We don't know of any other allocation procedure that gives more. And in the case of additive, we get the best possible guarantee with respect to this MMS hat, and hence it's also a simultaneous guarantee for all feasible shares. So even if, so it means that we have an allocation that even if the agent, after seeing what they get, says, oh, you know what, now I really would have liked to get an approximation with respect to some different share, but this share is a feasible share, you still get an approximation ratio of half, no matter what share they try to look at, as long as it is feasible. Okay, and I'll end here. Questions? So in this game, So the guarantees are given to an agent regardless of what other agents do, and also regardless of collusions between them, and also regardless if they can join together. Let's say, okay, I have entitlement 1/3, another person has entitlement to 1/3. Let's join together. We all have entitlement 2/3. We have more flexibility in the bidding. We'll try to bid against this agent who's using the safe strategy. Still, the safe strategy would work. So, I mean, so the notions here are such that we don't care what the other agents do, including collusion and joining together, breaking into other agents, smaller sets of agents or whatever. Yeah. Yes.
This guarantee side, if the procedure has to be a bidding game, like 1/3, can you do it?
Okay, so we don't know, but for the subadditive case, the log M over log M is tight, even for XOS, even for functionally subadditive, you cannot do better with the bidding game. And maybe, so this is not completely done yet, maybe even tight up to the constant factor in front of it. I think the constant factor should be probably 1, but yeah.
So,
Yeah.
There's still hope to improve 1/3 by finding a better strategy in the bidding games.
Yes, I think there's still hope. Sorry?
That will also improve the best one for him.
Yes, this would improve the best for MMS, yes.
So I wasn't sure what you answered about the
Okay.
what you answered about the computation for APS for additive valuations can be computed with polytime.
The APS?
Yeah.
So you can compute okay, in weekly polynomial time, like if the values are, let's say, integers bounded by a polynomial, you can compute it in a polynomial time. If the values of items, then you can compute the APS in polynomial time.
Okay.
Or if you have more generally, yeah, okay, yeah, weekly polynomial time, and it's also weekly polynomial, like a weekly NP-hard.
I had one more question. I mean, like, why a bidding game in the sense that, like, I mean, is there some intuition as to why the best guarantees in this case come from a bidding game? So this is not true for MMS, for example, right? So there we have explicit algorithms. So what is the intuition for?
So I think my intuition is that this is what we know how to analyze, and if we would know how to analyze other things, we'd find better approximation ratios. And this is specifically true for, let's say, XOS valuation functions, where we have constant factor approximations in the case of equal entitlement, constant factor approximation of the MMS, and in the bidding game, in the case of equal entitlement, you cannot get a constant factor approximation. So it's not that the bidding game is the one that will give you the optimal guarantees ex post, but just with our proof techniques, we don't know how to prove anything better now. Yeah.
So the techniques also say something about Pareto optimality?
About
Pareto optimality?
Not necessarily, no. It doesn't imply that the allocation at the end is Pareto optimal.
Yeah. Okay, but it does have sort of a price-based interpretation, which can.
But it's like an online pricing thing. It's not just one price that you see at the beginning, and then it's not like a competitive equilibrium or something like this. It's an ongoing game. So you can ask maybe what happens in equilibrium of this game, whether in that case it would be Pareto optimal, but I doubt it. I don't know. I don't know, but I don't see any reason why it should be. Yeah.
So the MMS hat, like, correct me if I'm wrong, so you say that, so MMS hat dominates every feasible share?
Yes.
In the, like, in the weighted setting, right?
Yes.
Do you have any, like, dominating guarantees for APS in the arbitrary entitlement setting?
So APS approximates MMS. No, it's not. It's not. You don't have any guarantee for the APS. So an example would be. So here's like an example. Suppose you have more than half the entitlement. Okay. So how much you're entitled to get? So according to MMS head, you round your entitlement to 1, so you're entitled to everything. You might say this does not make sense, but it does make sense because let's say in politics, if you have more than half the parliament, you can decide on all the rules, like you get to decide on everything. It's not that you have to give something to, I don't know, the opposition parties, at least not in Israel. Okay, so in some situations, if you have more than half the entitlement, you really have everything. So this is what happens with the MMS head. Then under the APS, you will not have everything in this case. You need to give things away. So, and in particular, let's say if there's just one item, under the MMS head you get it, and under the APS you don't get it if you have more than half the entitlement. You're not entitled to it. Okay, so in this respect, the APS does not approximate MMS head. So, so for this reason, it does not dominate all feasible shares.
So you actually have a feasible share example. Okay, so yes, that is feasible in this instance.
Yeah. So if you have half the share that says if you have more than half the entitlement, you get everything, and otherwise you're not entitled to anything, is a feasible share.
Thank you.
Okay. Yeah.
So it is like the MMS, it's MMS still that like, which is that you round down BI to the, not to 1/k, but to, so that is dominated by APS.
Yeah, if you round down instead of up, even then you dominated by the APS, but rounding up, you're not. And they're in a sense incomparable because let's say your valuation was, your entitlement was 1/k, then MMS had, you get to keep your original entitlement, and the APS is larger than the MMS. So they're incomparable, the APS and MMS head.
Okay.
Study MMS had beyond additive, I guess.
Yeah, I think it can be interesting, yeah. So the question was whether it would be interesting to study MMS head beyond additive valuations. So in principle, yes. Yeah.
Okay, are there any other questions? Okay, so let's thank Professor Feige for the nice opening.
Thank you.
So we break for coffee now?
Still copy.
Yeah.
Little bit.